In this section, we're going to discuss systems of equations and solving systems of equations by graphing. All right. But first, we wanted to give a simple definition of what a system of equations is. It's basically, if you want to think about it kind of informally, a group of equations. All right. That's all I mean. That's the only thing I mean when I say a system of equations. I'm just putting these equations together, I'm grouping them together, and I'm calling this a system. There are times in mathematics where we're going to actually need more than one variable to actually solve an application problem. And in order to solve an application problem when it involves more than one variable, we're going to need more than one equations, more than one equation. And so this is where those system of equations come into play. I have an example of a system of equation here. We have 6x plus 5y equals 28 and 3x minus 4y equals 15. I'm grouping those together. I'm calling that my system of equations. All right. Our goal in this section is to learn how to solve these things by graphing. But before we actually learn how to solve them, we need to know what their solutions are going to look like. Of course, you see an x and a y. All right. And our solutions to these things are going to involve x and y. And normally when we have an x and a y, we put it as an ordered pair. And so solutions to systems of equations are going to be the ordered pairs that satisfy, and this is the important part, satisfy each equation in the system. All right. So your set of ordered pairs are your ordered pair that satisfies each equation in the system. All right. Now, it can't just work for one equation, it has to work for both, all right? So it has to satisfy both of those equations. Let's look at an example where we verify or determine if an ordered pair is a solution to a system of equations. In this example here, it says, is the ordered pair negative 2, 9 a solution of the given system of equations? All right, I have 3x plus 2y equals 12 and y equals 1 minus 4x. All right. Now, some people may be able to look at it, but I'm actually going to, substitute my x and my y into both of these equations here and see if my equation remains true. All right. So instead of having 3x plus 2y equals 12, I'm going to have a 3 times a negative 2 plus 2 times 9. And I want to determine if that equals 12. Okay. Well, 3 times negative 2 is negative 6. 2 times 9 is 18. And that does, in fact, equal 12, right? So I'm halfway there. Now I'm going to check to see if negative 2, 9 is a solution to my second equation. Y is 9, so I get 9 equals 1 minus 4 times negative 2. Well, I want to see if that remains true when I simplify. So I get 9 equals 1. Well, that's a negative 4 times negative 2, which is plus 8. And 1 plus 8 does equal 9. All right, and so yes, this ordered pair, negative 2, 9, would be considered a solution to this system of equations because it does satisfy both of those equations. Had that one of these been false, either this one or this one, had one of those been false, then we would say no, that this ordered pair would not be a solution to the system. One of the ways to solve these systems of equations is by graphing. Okay, and we're going to look at actually multiple ways to solve a system of equations. Graphing is kind of going to be simple here because we're talking about lines, right? We have x plus 5y equals 5, x minus y equals negative 7. These are two linear equations. And so by now in your mathematical career, you should know how to actually graph linear equations. You can graph by plotting points. You can graph by using the slope and the y-intercept. You can graph by using the x and the y-intercept. As long as you can find 2 points that the line goes through, draw your line and you can draw the lines in the system. And actually where those lines intersect is where our solution is going to be. Let's look at this example. All right, I'm going to just stick mainly to the method of using the slope and the y-intercept to graph these lines. So what I'm going to do is I'm going to write each equation into y equals mx plus b form. All right, for me to do that, I can subtract x from both sides. I want to solve for y to get into y equals mx plus b form. I'll be left with 5y equals And just so I get it into y equals mx plus b form, I'm going to write the x first. So instead of writing 5 minus x, which is fine, I'm going to write negative x plus 5. Then I can divide both sides by 5, and I'll get y equals. Now, when I divide those things by 5, I can separate, since 5 is my only denominator. That's a 1x over, negative 1x over 5. So I can write that as a negative 1/5, so I can actually see my slope, x. And 5 divided by 5 is 1. This gives me that my slope is negative 1/5. I'm going to put that negative with the 1 on top. And my y-intercept is 1. Okay? So if I wanted to graph this line, all right, I'll actually come back and graph. Let's look at the other line. We have x minus y equals negative 7. All right, I'm going to get into y equals mx plus b form. So again, I'm going to subtract x so I can get my x or my y isolated on one side by itself. I get negative y equals, again, I'm going to write negative x minus 7. And then I can divide both sides by negative 1. So I'll get y equals. Now when I divide, everything in these, the negative x gets divided by negative 1, which makes that a positive x. And negative 7 gets divided by negative 1, which makes that a positive 7. And so in that example, my slope will be considered 1, or I'm going to write it as 1 over 1 so I can see my rise over my run. And my y-intercept is 7. So I'm going to go to my graph and I'm going to graph these two lines. Okay. And when I graph these, I'm going to be careful so that I can actually see where these lines meet, because that's where my solution is going to be. All right, it has a y-intercept of 1, right? That's the point 0, 1. So I'm going to my graph. 0, 1 is here. And since my slope is negative 1 over 5, then if I go down 1 and right 5, I'll be back on my line. So I'm going to go down 1 and to the right 1. So I'm going down 1, go to the right 1, 2, 3, 4, 5, and I have another point on my line, the point 5, 0. All right, I can do that again. From this point, I can go down 1 and to the right 5, 1, 2, 3, 4, 5, and I have the point negative, positive 10, negative 1. Okay. If I wanted to go the other direction, notice I put the negative on the 1. I could have written this as 1 over negative 5. Had I done that, right, instead of going down 1 and right 5, I could have went up 1 and left 5, right? So the top number tells you to go up or down. Positive is go up, negative go down, and the bottom number on my fraction tells me to go right or left. If it's positive, go right. If it's negative, go left. So I can actually go from, let's say I go from this point, my y-intercept, I can go up 1 and to the left 5, 1, 2, 3, 4, 5, and I have another point on my line. And then again, I can go up 1 and to the left, 1, 2, 3, 4, 5, and I have another point on my line. And then I can connect my dots as best as I can. And I have my line. All right. Let's do the same thing for our other line. Right. Our y-intercept is 7, the point 0, 7. So I'm going to graph that here. And I can go up 1. Right. That's positive. And my denominator is positive. So I can go to the right 1. Okay. So I go up 1 and to the right 1. Up 1 to the right 1. If you notice, I'm not getting any closer to my actual solution. My solution is where the ordered pair that satisfies both of them is where they intersect. And so instead of going up 1 and right 1, we can do something clever here, right? I don't see a negative, but a negative 1 divided by negative 1 will give me the same slope. It's still positive 1. Negative 1 divided by negative 1 is still positive 1, which is sitting here, right? And so instead of going that direction, we can go down 1 and to the left 1. All right, so from my y-intercept, I'm going to go down 1 to the left 1, 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 down one to the left one. And once I hit that, I can draw my line and I'll see that I actually do intersect at a good point. So this point right here is my solution. It's where they intersect. And that point right there is the point -5, 2. That point right there is the point -5, +2. So here is my solution. Okay. Again. So when we have a system like this that has one solution, the solutions is where they intersect. We call this type of solution an independent solution. The equations in this system is independent. That's just a vocabulary term for something that happens like this. Let's look at another example. In this example, we have 4x plus 6y equals 12. Y equals -2/3 x plus 2. And again, we're going to solve the following system by graphing. All right. Again, I'm going to start by getting into y equals mx plus b form. Again, this is not the only way that you can graph these lines. You can graph these lines by getting them by plotting points, finding the x and y intercept, whatever method you're most comfortable with. All right. Use that method to help you solve or graph these lines. All right. Again, I'm going to stick with the slope and the y-intercept. So I'm going to have to actually solve these equations for y. All right, the second one's already solved for us. But here we go. We get 6y equals, again, I'm going to do a -4x plus 12. And then I can divide both sides by 6 to get that y isolated. So if I divide this side by 6 and this side by 6, I'm going to get y equals, I'm going to take my time here. I'm going to go ahead and divide both of those by the 6 so that we can see what's happening here. Because we're going to have to actually simplify a little bit. Now that -4/6x, all right, 6 and 4 have a common factor of 2, so that's actually -2/3 x. And 12 divided by 6 is 2. So in this case, we get a slope of -2/3. Right now, I'm going to attach that negative with the 2. And we're going to get a y-intercept of 2, or the point 0.02. All right, so that's our first line. Let's look at graphing or solving for y in our second one. We got y equals -2/3 x plus 2. And actually, it's already solved for y, so we can tell what our slope is. All right, so our slope in this example is -2/3, and our y-intercept is 2. Wait a minute here, right? If you look, both of these equations are exactly the same. They have the same slope, they have the same y-intercept, so when we graph it, it's going to be the same line, right? So although it looked like we had two separate, distinct lines in this problem, they're actually the same line, but they're given in different forms. That's why it's important to graph so that you'll know. And let's see what happens when we actually get our solution. All right, remember, when we graph using this method, we start with the y-intercept, which is 2. And then by our slope, if I attach the 2 to the negative to the 2, I can go down 2 and to the right 3. All right, so down 2 and to the right 3, I get my point 30. And since this is the same line, I'm not going to worry about doing the slope much more. I'm going to go ahead and draw my line, since it's actually going to be the same line. And I have my line graph here. Now, what we said before is our solution is the ordered pair where our lines intersect. And actually, these lines intersect at all the same points, since they lie on top of each other. And that means every single point that's on this line is a solution. All right? Whenever this happens, we call this type of system dependent. This is a dependent system. All right. It occurs when the lines are the same. Okay. Graphically, we say the lines lie on each other or on top of each other. That means we have infinitely many solutions. All right, there's infinitely many solutions to this dependent system. Now, we can't say that our solution is all real numbers, all right, because all real numbers is on the number line. This is actually in my XY plane. When we write our solution here to this example here, or this problem here, we always write it as an ordered pair given in terms of the variable x, right? So my variable x is my variable x. Instead of writing y here, we're not going to write y, so let me go ahead and erase that. What we're going to do is we're going to go to see what y equals in the equation form. Sorry about that. Okay. In my equation, I have y equals negative 2/3 x plus 2. Same thing here, negative 2/3 x plus 2. So instead of writing x in that ordered pair, I'm going to write negative 2/3 x plus 2. And this gives me my solution for all x. All right, that means you give me an x value, I can tell you a point that is a solution to this system, because all I have to do is plug in that number for x here into my x coordinate and plug it in here for my y coordinate. Okay, and this is going to happen every time when we have a dependent system. Let's look at another example. We have y equals negative 2x plus 6, and then we have 10x plus 5y equals 15. Again, same process. I'm going to come here. This one's already solved for y, which is nice. Our slope is negative 2. I can write it as negative 2 over 1. And our y-intercept is 6, or the point 0.06. Have 10x plus 5y equals 15. I'm going to solve this for y. First thing I'm going to do is subtract 10x from both sides. I have that 5y equals negative 10x plus 15. I can divide both sides by 5. When I divide by 5, this is nice. Everything goes evenly. I get a negative 2x plus 3. So my slope is negative 2. I can write it as negative 2 over 1. And my y-intercept is 3, or the point 0.03. So what I'm going to do is I'm going to go to my graph, and I'm going to graph this line. Has the first line here has a y-intercept of 6 and a slope of negative 2. Well, wait. This line here also had a slope of negative 2. So from my knowledge of graphing lines, these two lines are going to be parallel, right? Which means they're not going to meet. All right, so let me draw them so I can make sure that that's actually going to happen, even though I think that's what it is. So I got a y-intercept of 6. I can go down 2 into the right one. Down 2 into the right one. And I have another point on my line. All right, so I've got 3 points. I think that is pretty good to go. And then I'll extend it in both directions. My second line, this one right here, has a y-intercept of 3 and a slope of negative 2. So I'm going to go down 2 and to the right 1. Down 2 to the right 1. And I have some other points. And as I can see, these two lines are parallel. All right. When this happens, all right, our solution is where they intersect. Well, since they're parallel, they don't intersect. That means I have no solution. Anytime this happens, we call this type of equation or this type of system inconsistent. Okay? It occurs when there is no solution. Graphically, the lines are parallel. And we always know that parallel lines don't intersect. Okay? And so what we're going to write here is that we have no solution in this example here. Okay? And this concludes our lesson on solving systems of equations by graphing.